Hello and welcome to Advanced Hydrogeology, Geo 572, Lecture 2 on mathematical modeling and analytical solutions to partial differential equations. So today we're going to take our first step into thinking about how we use partial differential equations to model a process in earth sciences and some of the ways that we can solve partial differential equations to predict behavior. So I'm going to go ahead and share my notes here. And we're going to discuss mathematical modeling. So let's start off by considering a mid-ocean ridge. If I can get my trackpad to connect here. All right, we're good. Okay, so let's pretend here that we're at a mid-ocean ridge. All right, and at a mid-ocean ridge, hot mantle is upwelling. Well, let me put the ocean up here. Gonna want that. And we'll put a little whale here for scale. That's a really big whale, biggest whale ever. Okay, so hot mantle is coming up and it's forming brand new crust, right? And this crust moves away from the mid-ocean ridge on either side, all right? And so we've got this process where this hot mantle is cooling in these zones here and then forming rocks. All right, and we're going to think about a model of this process right here. We're going to focus in on this zone right after our liquid hot magma has cooled into a rock. All right, so I'm going to draw another picture here and I'm going to focus in right here in this zone. And now we're down again, we're at the bottom of the ocean and we've got this brand new crust, right? That just solidified. Okay, and I'm gonna think about a temperature profile of that crust. All right, and here's 1,000 Kelvin, which is roughly the melting point of basalt. And so we can think of this crust here as a newly formed layer of basalt. And right after it cools, it's all at 1,000 degrees Kelvin. So if I was to look at a temperature profile, I would get this straight line with depth. So here's depth increasing. I get this straight line at 1,000 degrees Kelvin, all right? And this is right after it cools. Now, this ocean here above my profile, right? It's not at 1,000 degrees. It's at like 4 degrees Celsius. All right, it's cold. And so immediately after forming, we know that the top of our oceanic crust here goes right at the skin, it goes to something like 4 Kelvin, right? It goes to the temperature of the ocean. All right, and so what we want to do is think about how this temperature profile evolves in the oceanic crust. And I know what you're thinking right now. You're thinking, oh my gosh, this is supposed to be a hydrogeology class, and Peyton's talking about cooling of the oceanic crust after a mid-ocean ridge. And that's what's so awesome about this class. But let me tell you, it will eventually have something to do with groundwater. All right, so it's this process that we're interested in. The top of my oceanic crust moves to 4 Kelvin. And what I want to do is be able to predict or model what the temperature profile in this basalt looks like through time. So at some time in the future, let's say this time here is T0, my initial cooling time. And this is some time here, T sub I, sometime later. And I want to be able to predict what this temperature profile looks like in my basaltic crust, right? And so the process that we're going to do to be able to make this prediction is mathematical modeling. And to do that, we're going to solve a partial differential equation. All right. So let's think about what this slab looks like right after it cools. What we have is this uniform slab of a constant temperature, 1,000 degrees Celsius. And there is one temperature at the top and one temperature at the bottom. But that temperature, you know, if we look in map view of the mid-ocean ridge, so here this is cross section. All right. If I look in map view, all right, remember that my mid-ocean ridge is this ridge that's really laterally consistent. And so that it's really, I would have this slab extending a long ways in either direction. And what I'm interested in is this point here, not close to any boundary, but right in the middle, right after it cools, right after my liquid hot magma cools. And I want to model this temperature in the slab as the slab moves away from the ridge, right? And if I do that, I can see that this thing's symmetric on either side. It looks the same on either side. And so I can really think about temperature movement in one dimension. I can think about this as cooling or instantaneously cooling of this semi-infinite half space, all right? It extends in either direction, starts off at a certain temperature, and as it moves, it's pretty homogeneous in all directions. So we can think about this actually as a one-dimensional problem, all right? So this problem gets boiled down to 1D. And we can think about this step change happening very rapidly, right? I cool this magma, and then my rock is all at 1,000 degrees, and then it gets exposed to cold ocean water, and that immediately cools the top, all right? Now that isn't exactly what happens. The temperature at the top probably cools a little more slowly than instantaneously, but part of what we're doing here is thinking about how we simplify our problem into something that we can mathematically model. So we're going to call this 1D instantaneous. Instantaneous cooling of semi-infinite half space. And what that means is that we're gonna model this as a process where we have a slab of constant temperature, right? A 1D line of constant temperature initially, T naught, all right? That extends infinitely in depth, all right? And right at the surface, at time T naught, the temperature changes from 1,000 degrees to 4 Kelvin, all right? So start temperature is T naught, 1,000 Kelvin, at initial time T naught. And then at and T naught is T equal to 0, all right? At T equal to 0, all right, at this initial time, and Z equal to 0, all right? So the top of my domain, my temperature goes to T surface, all right? And the other thing I'm going to say is this thing's really deep, really deep. So at Z equals to infinity, all right, my temperature is going to stay constant. T is equal to T naught for all times. Okay, so this is my mathematical model. I'm saying it's a 1D cooling. We're starting off at an initial temperature, and then this temperature at the surface is changing. And the temperature at great depth is staying the same. So I figured out some simple way to mathematically describe what's happening that simplifies the physical process. That's the mathematical model. So let's go about trying to use this model. So the first thing we need is a governing equation. We need to have an equation that describes the evolution of temperature. And I'm not going to derive this equation, but I'm going to write down the one-dimensional heat flow equation. One-dimensional heat flow equation. CP, that is the specific heat of the rock. That means how many joules of heat do I need to change the temperature 1 degree. dt, all right? The change in temperature with time is equal to kth d squared t dz squared. All right, this guy. So CP is the specific heat. And it is the number of joules required to heat 1 kilogram, 1 degree Kelvin. Joules per kilogram Kelvin. All right. This guy here, KTH, is the thermal conductivity. And it relates the temperature gradient to the heat flux. All right, so we've got this other, let's take a little aside and talk about Fourier's law. Which says the thermal heat flow, QTH, is equal to negative K, TH, dt, dz. Fourier is spelled differently. Let's see if I can get this to work. Fourier's law. All right, Fourier's law looks a lot like another law we've already talked about, and that is Darcy's law. It's exactly the same. All right, and K relates the temperature gradient to the heat flow. All right, heat flow or heat flux here is in watts per meter squared. And so our unit of our thermal, this guy is in watts per meter squared. This is Kelvin per meter. All right, so the unit to make these two sides equal of thermal conductivity is watts per meter Kelvin. All right, so then I'll have meters squared, Kelvins will cancel, and I'll end up with watts per meter squared on either side. All right, so this guy's in. What is happening? Wow. Sometimes my pad gets a life of its own. Watts per meter Kelvin is the unit for this. All right, so a couple things I want you to see here. Fourier's law. Is exactly like an analog of Darcy's. Okay, and the heat flow equation has the same form. Same form as groundwater flow equation. All right, both of these equations, all right, say the change in temperature with time or the change in head with time is equal to the curvature of the temperature field or the curvature That's the second derivative of the head field, all right? This form of equation is called a diffusion equation, and it crops up in many physical processes. The ones we're going to talk about in this class are heat transport, chemical transport, diffusion of chemical species, and groundwater flow, all right? Okay, so what I want to be able to do is solve this heat flow equation, all right, and be able to model the temperature with time in my cooling slab. All right, so to do this, we are going to solve the boundary value problem. All right, and this is a solution to a partial differential equation, like our governing equation up here, the heat flow equation. This one is a partial differential equation, a PDE. All right, solving the boundary value problem will give us a solution to our PDE subject to our boundary conditions. All right, and one of the things, a lot of this class is basically going to be focused around solving the boundary value problem. That is what groundwater flow modeling is, all right? We're seeking if not a true solution, an approximate solution to a PDE subject to our boundary conditions. And we need a series of ingredients to solve it. All right, we need a governing equation. We need boundary and initial conditions. We need a domain of interest. All right. We need controlling parameters. All right, so if I go back to our initial thing we're trying to model, that's cooling of this oceanic crust. All right, our governing equation we have, that's the heat flow equation. So for our model, we have one is the heat flow equation. All right. Our domain of interest is a 1D line. from 0 to infinity. Our initial condition, right? That's the state of the system at startup or at time 0. T is equal to T naught at T equal to 0. All right. Boundary condition. We have two boundary conditions. That is T is equal to T surface at X equal to 0. T greater than equal to 0. So for all times at the surface, temperature is equal to Ts. And that's one. And our second one, T is equal to T naught at X equal to infinity for all times greater than 0. All right, so those are our two boundary conditions. Okay, our parameters that control the solution are kth and Cp. All right, so we need to know all of this in order to solve our equation. So this, this is an important thing that we've done. First of all, we've taken this problem, all right, cooling of oceanic crust, and we've come up with a way to simplify it, right, by looking at symmetry and saying, well, I think I could approximate this just by one-dimensional cooling. All right, we've decided what the conditions are at the boundaries of our domain. So we came up with the domain, we decided what the conditions were at that domain, and we came up with the physical things that we're interested in, and that for us right now is one-dimensional conductive heat flow. All right, that process of taking this complex geologic system and reducing it to something that we can describe, and with all these conditions, is the conceptual model stage. All right, and now what we've done is, in order to build all the ingredients to solve the boundary value problem, develop the governing equation, develop the boundary and initial, the domain of interest, and the controlling parameters, we've built our conceptual model, and we're developing a mathematical model that will allow us to describe temperature in our plane or in our slab. Okay, so what we got to do now is solve this equation subject to these boundary conditions. And to do that, we're going to do a process called an analytical solution. So developing an analytical solution. Okay, so we've got our boundary initial conditions. We've got our one-dimensional heat flow equation. I'm going to do one thing to this heat flow equation. I'm going to take the thermal heat capacity and I'm going to divide it over. I'm going to divide both sides by the heat capacity here. So our equation is going to end up looking like this. dt is equal to alpha th d squared t dz squared. And this guy alpha now is the conductivity over the heat capacity. This is essentially the conductivity over the storage. All right, we're going to use this in water too, and we call that the thermal diffusivity. All right, remember this, conductivity over storage gives us diffusivity. All right, so we're going to solve this equation using a process called similarity. Okay, so we're going to solve using similarity. And similarity is basically just creating dimensionless or normalized variables that allow us to reduce the number of variables here. So the first thing we're going to do is define this thing called dimensionless temperature. And what it's going to be is T minus T naught divided by Ts minus T naught. All right, and all this is a normalized temperature, all right? It just compares the current temperature to the total temperature change. All right, so we can just, it's just a normalized temp. Okay. So let me, now I can rewrite my equation up here in terms of normalized temperature, all right? D theta dt is equal to alpha th d squared theta dz squared, all right? Okay, so we'll call this 1. All we've done is just, this is just a linear mapping on temperature. So the same equation, we're just changing temperature to vary between 0 and 1 basically, but it's the same equation. All right, let's think about our boundary conditions now. All right, well, at our temperature, all right, at all depths at a time of 0, all right, that would be the temperatures everywhere at time 0, right? That's our initial condition, would be T naught. So we would have T naught minus T naught over Ts minus T naught. So this whole thing would go to 0, all right? I'd have T naught minus T naught here. This goes to 0. So theta is equal to 0. That's my initial condition. All right. At the top of my boundary condition, for all times greater than 0, I'm going to have this equal to Ts. All right. So I have Ts minus T naught, Ts minus T naught. Theta equals to 1. Okay. Then at infinite depth, all right, at infinite depth, my temperature is equal to T naught, the initial temperature. So I have T naught minus T naught again. Okay, so at depth, at Z of infinity, for all times, my temperatures, or my dimensionless temperature is equal to 0. All right, so boundary condition 0, 1, 0. Okay, so that is step 1, dimensionless temperature. Okay, step 2, dimensionless distance. Okay, so we're going to define this thing. We're going to call it eta, all right? And eta is going to be our distance, z, divided by 2 times the square root of alpha th times time. All right, let's think about what this is. All right, first of all, what are the units here? So remember that alpha th is well, let's look at the unit. So alpha th is equal to the heat capacity, which was joules per kilogram Kelvin, and divided by the thermal conductivity, which was watts per meter Kelvin. All right, so this is equal to joules per kilogram Kelvin times meters Kelvin over watts. All right. So alpha th has units of, these guys cancel. Um, hang on. Oh yeah. So what we got to do here is remember what a joule is. All right. So a joule is equal to a watt, or or we'll remember what a watt is. And a watt is a joule per second. So let me erase this. Yeah, all right, sorry. Just had to remember some basic physics here. So a watt is a joule per second. So this becomes joules per kilogram Kelvin times meters Kelvin second over joules. And so my joules are going to cancel, my Kelvin is going to cancel. Something's not right. My seconds should cancel too. All right, let me pause and I'll figure this out and I will come back. Okay, I remembered what's wrong here. Our thermal diffusivity. Okay. Okay, if you didn't get that, Sunday, this Sunday, Indy and Nick, and maybe me, are going to watch the European Championship in soccer at the Mar-Bar. All right, sorry. Okay, here's where we went wrong. Thermal diffusivity is the thermal conductivity divided by the heat capacity times the density. All right, and that's good because that's going to get us where we want to go. So let me just redo this guy here. Okay. All right. Oh, golly. All right. So joules per kilogram Kelvin divided by kilogram per meter cubed. All right. This whole thing's messed up. All right. Watts per meter Kelvin. K over kilogram per meter cubed joules per kilogram Kelvin. Okay, this is joules per second over meter Kelvin, kilogram per meter cubed, joules per kilogram Kelvin. All right, kilograms cancel, joules cancel, Kelvin cancel, and meters go up here. So we end up with meters squared per second. That is the unit of thermal conductivity. Okay, so what is this thing now? Well, now the unit of alpha, th, times time is meters squared per second times time second. All right, so these two are going to cancel, and the square root of that is going to give me a unit of meters. So this guy gives me meters over meters. All right, so this is dimensionless. Time or distance. All right, it's a distance normalized by this distance that's given by the square root of our thermal diffusivity times the time. We're going to learn that that's a really cool distance, but for now it's just a distance we normalize by. We divide our depth by this distance. All right, and we're going to get a dimensionless distance. All right, so we want to write our governing equation in terms of theta and eta. All right, so let's think about how we might come up with our first term of the equation. So the left-hand side, right, this is d theta dt, all right? And we're gonna use the chain rule to say that's equal to d theta, d eta, d eta dt, all right? And this is equal to d theta, d eta, all right? And now d eta dt, all right? Well, all we do is we come up here and we take the derivative of eta with respect to t. And if you do that, you end up with negative z over 4 alpha over square root of alpha t cubed. And if you do some algebra, this reduces to 1/2 eta over t times d theta d eta. All right, so d theta dt can actually be written in 1/2 eta over t d theta d eta. So we're going to remember this as star. Oh, I don't need that. Okay. So now I want to do the right-hand side. D squared theta, d eta squared. Oh, sorry, dz squared. Okay. Chain rule again. D squared theta, d eta squared, d eta dz squared plus d theta d eta d squared eta dz squared. All right, well, d theta d eta, all right, if we go back to our definition of theta, it has nothing to do with eta, so this term goes to 0. All right, and we have this guy here. All right, and we can take the fact that we know we can take the derivative of eta with respect to z, all right? And that's just going to end up being 1 over this. So d eta dz is equal to 1 over 2 square root alpha th times time. All right. And now d eta dz squared, all right, well, we would take the derivative with respect to z of d eta dz, all right, and there's no eta in this term, so we're going to end up with d squared eta dz squared is equal to 0, all right? That's just taking the derivative of the definition of eta with respect to z once and twice. All right, so that gives us our second important equation, and that is d squared theta dz squared is equal to d squared eta dz, well, sorry, it's not what it equals. It is equal to d squared theta d eta times this guy, so we're going to get d squared theta, oh, d eta squared times this guy, which is this squared. 1 over 4 alpha THT. Okay, so this is double star. All right, and now we can write our left hand and our right hand equations, our left hand side and our right hand side. And we have -1/2 eta over t d theta let's go up here, d eta is equal to alpha over 1 over 4 alpha t d squared theta d theta squared. Now, I did these with regular d's, and there's an important distinction between these two. These guys, all the derivatives are in terms of eta. So this is now an ordinary differential equation and much easier to solve than a partial differential equation. All right, so I can do some algebra and I get eta d theta d eta is equal to 1 over 2 alpha d squared theta d eta squared. And I know that theta of infinity is equal to 0, and I know that theta of 0 is equal to 1. Okay, we're getting close. So now we're going to do substitution. Phi equal to d theta d eta. It's called substitution. I can rewrite this as negative eta phi is equal to 1 over 2 alpha d phi d eta. All right, and I can solve this guy by integration. So first of all, I'm going to separate it. I'm going to move this over to this side and this over to this side so that all variables of eta are on one side, all variables of phi are on the other, and then I can integrate. So all right, I get these two. I'm going to integrate them. All right, so the integral of this one is negative eta squared. The integral of this one is the natural log of phi. And this is all going to be plus some constant, C1. So I took all this negative and this business here, and I lumped it into this constant of integration. All right, so now I can go another step. Phi is equal to C1 e to the negative eta squared, right? I just took the exponent of both sides. And remember, phi is equal to d theta d eta. Okay, so I'm going to integrate again. Theta is equal to the integral of d theta d eta d eta, all right, which is equal to the integral of this guy, C1 0 to eta prime e to the minus eta prime d eta prime. All right. Okay. Now, this is going to be plus C2. All right. Now, I know that when if I apply theta equal to 0 is equal to 1, right? I'm going to do this integration, and you end up that this implies that C2 is equal to 1. All right. So I have theta is equal to why? I mean, the reason why this is, if you're wondering, if this is 0, you're integrating from 0 to 0. There's no area under this curve, no matter what it is. So this term will be 0. So this has to be 1 in order for theta of, or eta of 0 to give us a theta of 1. All right. Okay, so we're going to use now our other boundary condition. So we know that theta of infinity is equal to 0. All right. So that is 0 is equal to C1, the integral from 0 to infinity, right? Eta, plugging it in here, e to the minus eta squared d eta prime plus 1. All right. This is an identity. All right, and you can look this up in an integral table, but e to the minus eta prime, if this is infinity, this goes to this guy, this integral goes to square root of pi over 2. All right, and so if this implies that C1 has to be, if this whole thing's going to be equal to 0, C1 has to be equal to negative 2 over square root of pi. That will make this whole term negative 1 plus 1, and we'll get 0. All right, so finally, we get this. Theta is equal to 1 minus 2 over square root pi, the integral 0 to eta e to the minus eta squared d eta prime. And this is a special integral. It's called the error function, ERF of eta. And it turns out that 1 minus the error function of eta we call the complementary error function. And that we write as ERF C of eta. All right, this is a well-known integral, pops up a lot. All right, and so we get our final solution. Theta is equal to ERF C of eta. And now I'm just going to substitute in my definitions for theta and eta. And I get T minus T naught over TS minus T naught is equal to ERF C Z over 2 square root of alpha TH T. And this is a solution to our partial differential equation. It obeys all these derivatives here, dt dt and d squared t dz squared, all right, subject to these boundary conditions, all right? And we know that when we put z equals to 0 in there, we'll get the right answer. And we know when we put z equals to infinity, we'll get the right answer. All right, so this is called an analytical solution. And I hope you get a feel for how much sort of calculus goes into producing one of these analytical solutions. And I'm going to tell you that you can only produce these solutions for the very simplest of equations. So here we have one-dimensional heat flow, all right? We're not considering any other dimensions. We're saying that the thermal conductivity is constant and the heat capacity is constant. And we've implemented very basic boundary conditions, right? These step changes in boundary conditions. All right, so these analytical solutions, now we can use this, all right? We can plug any value for T in, any value for depth in, and we can calculate the temperature. Okay, so as I was saying, this will allow you to calculate the temperature at any time and any place along the line. And so we have an analytical solution, we have a mathematical model, we can predict and calculate the temperature distribution. So This is the first way that you try and get a solution for any partial differential equation. If you have an analytical solution, it's the best, but they can only be created for simple problems. All right, thanks. Have a good night. We'll talk to you later. Bye.